So, welcome everyone to Guided Study Group Week 12 of Math 141. So, hopefully everyone have a great midterms and we are now ready for the materials for final exam. So, starting from for the final exam, the main materials is going to be on power series and related stuff. So, I think it's power series and we have a small sections of polar coordinates and parametric equations, but yeah, that's just a quick hint about what we're gonna looking for in the next few weeks. So today we'll be looking at sections 11.8 and 11.9 power series, and the other one is representation of a function as a power series. So first off, power series, I would say is a kind of throughout the semesters I've been teaching this. I think this is a very challenging part to a lot of you, and so I think this session is the one that really need a lot of practice and kind of good documentations of what you're doing. And so power series is defined as the series from n equals 0 to infinity of Cn x to the n, with C be like the coefficient in front of every single term of xn. So it's going to be CO plus C1 to x multiply x to the 1 and C2 multiply x squared, so on until you get to xn. So this function is the sum of sum of all terms in all of these terms. Has its domain be the set of all x for which the series converges. So kind of it basically saying this series only makes sense when you have its converges, and you need to include those value of x. Those are when we call interval of convergence and radius of convergence. If you have all of the coefficient if you have all of the coefficient be 1, then you're gonna have it becomes something called the trigonometric series that we've seen before. And so it converges when you have x is between -1 and 1, and it diverges when the absolute value of x is bigger than or equal to 1. This one can be put as absolute value of x smaller than 1. Then we have the concept of power series central at A. Oh yes, this one we have something like the interval and radius of convergence. So having said that, we have this series, instead of just x to the n, now we have it be x minus a to the n. So this a now we call it as the center of the power series. Then we have a theorem saying for a given power series, there are only 3 possibilities. It will converge only at one value at the center, or it converges for every x, or it converges in a radius of convergence. So this part. So there only be 3 possibility for a given power series. So at least we know in effect that for every power series, we can always find at least one point where you have the series' convergence. Then you have this table. So to find the radius of convergence and the interval of convergence, we have kind of like a generic method is using the ratio test. So we use the ratio test now, kind of like recall us from midterm 2, where we have to use the ratio test, we had to find the limit of n approaching infinity of absolute value of the n plus 1 term in the sequence divided by the n term in the sequence. Now, to do that, after that you have that value, and to figure out what is the radius convergence. So recall again, if we have finding this limit in the ratio test. If the limit, so ratio test, if this limit is smaller than 1, then you have its convergence. So that's how we can apply all of them in. And again, to find the interval convergence, you're gonna generally take the open interval inside, and to check off the two endpoints. If you have the two endpoints, say you have here 2 and 4, when you plug in 2 into the sequence, see what series you end up with, and you maybe can use what you learned in midterm 2, like alternating series test or every one of those tests, to figure out if you're gonna take that point or not, which we're gonna see in the examples that we're doing here. So therefore, you have some of the problem that you can be asked in this sections is that find the radius and interval convergence of a power series. So first is find the radius conversion using the ratio and the root test. Then you can check back the series at the two endpoints of the interval to determine if you take it as an open interval or closed interval or half. So here you have the practice problem 1D. This is the first example. We're going to do that. Find the interval and radius of convergence of this series. So you have first have to find the interval convergence. You have find, I would say this one I'll use ratio test. So we have 2 to the n plus 1, x to n plus 1, divided by n plus 1 square, multiply n square, 2 to the n, x to the n. So this one, what we end up having is a limit of n approaching infinity. When you have n square over n plus 1 square, this ratio at n's approaching infinity is clearly 1. Then the other one is going to be just 2 absolute value of x. And so this is going to be 2 absolute value of x, and you need it to be smaller than 1. Therefore, you have absolute value of x to be smaller than half. So we have radius of convergence is half. Now, when we have, and you have the center is 1. The center is 0. So you're now looking at negative half and half. But now you have to figure out what is the thing outside. So when you have x equal negative half, you have the series become negative 1 to the n over n squared, which is going to give me 1 over n squared. And this is converges by, I think, p series, where you have p equal to 2. Another one, you check the other endpoints, then you're gonna have the series become negative to the n, half to the n over n squared. And this one is also converges because it's gonna be negative 1 to the n over n squared. And this one will be converges by alternating series test. Therefore, our interval convergence, we will take both of the endpoints. So here we're trying to figure out, is it an open interval or a closed interval, or is it half this thing and half the other one, right? And so the way that we figure it out is that we're gonna plug the number in and look at what we have, what we can do with it from the materials of midterm 2. And so we kind of have the general method now. Clearly, you can just first use the ratio or the root test to find that limit. and then you need it to be smaller than 1 to have a convergence series. Then you're gonna find the radius of convergence, and then you just figure it out if you're gonna take the two endpoints of that interval or not. This is a equals 0 is particularly important because it shows the fact that your series is centered at 0. So look at this interval, it's centered at 0, right? Symmetric around 0. That's what I want to say by the center of convergence. Now we're going to do the same thing for a kind of more complicated. So again, first step, I'm going to use ratio test or root test to find this ratio. So we're going to have limit of n approaching infinity to n plus 3, and then you have x minus 1 to the n plus 1 divided by 5 to the n plus 1 divided by 5 to the n to n plus 1 subvalue x minus 1 to the n. Okay, this one is going to equal, so you have here it's going to 2n plus 1 factorial is going to be 2n plus 3, 2n plus 2, 2n plus 1 factorial. So I can cancel out with a 2n plus 1 factorial in the denominator. So what we have left is 2n plus 3, 2n plus 2, and you have x minus 1 to the n divided by 5. Oh, not to the n, just x plus 1. Now very clearly, as n approaching infinity, this part is going to approach infinity as well. So to make sure that this thing end up with something smaller than 1, then absolutely you need this part to be 0, because that's the only way that you can have it for sure. So you have absolute value of x has to absolute value of x minus 1 have to equal to 1, or you have x equal to 2. No, not 2, 1, but 2, 0. And then you have x is absolutely equal to 1. Now, there we have the radius of a convergence is 0, and interval convergence has only one point, which is at 1. Now, this is because of the fact that there was a very dominant component in this final ratio is going to infinity. So if you want the entire fraction to be smaller than 1, eventually you need x minus 1 to be 0 all the time, at least. So you have to find that value. So it's kind of like the same thing, but it's a little bit more special. So, and here you have, here's when you have a equal to 1, center at 1. Now we're going to 11.9 power series representation, and I think this is kind of like the most challenging sections in the entire part of materials for finals, because I saw a lot of my students struggle in this in the previous year. So let's see how it works. So we asked you to manipulate or differentiate or integrate. So the general method to find the representation for a power series, or for kind of say like an expression and find the power series of that thing, is to manipulate, differentiate, integrate the sum of trigonometric series. Why did I say that? So we have a theorem saying if you have a power series like this, have a radius of convergence bigger than 0, then you have fx equal to that series is differentiable on the interval of convergence, at least in the open interval of convergence. And so we have f prime of x, meaning the derivative of f with respect to x is going to be the same series, differentiate. So Cn is a constant, so you always keep it. X minus a to the n, when you take derivative, is going to take the n out, and x minus 1 to the n minus 1. And we put a series sign here, meaning that you take derivative for every single term in that sequence. And note the fact here that when you take derivative, this starting n go back to 1, because now you have the power of n minus 1. So you have to start at 1. So therefore we have, because we don't usually start, because we don't account for x to the negative power. And this one is also equivalent. Another way to write it is, or you can have this one at dx of this series is going to equal the series of all terms in the sequence. Same thing if we take integral. If we take the integral, then you're gonna take integral of every single term. But note the fact here that your starting n doesn't change, because as long as the starting n is a positive number, so like the power here, the starting one has to be a positive number, then or equal to 0, then that works. But if it's a negative number, that's when we have to think about it. So here is another way to write this one, is that you rewrite this to be the series of all integral of the terms of integral. Now, during this integration and differentiation, why do I tell you this thing? Because after this, you can see in the example in the lectures and also in my upcoming example, is that a lot of the time when you find a power series representation of, say, like an expression, then you have to figure out, then you usually, well, I mean, at first now we're going to do the basic level, which we're going to derive like the regular or like the very basic expression. But then after that, usually you're going to be asked to do like at least one step of differentiation or integration of a function to find its series. So you go from a basic to the complicated one. And during this integration and differentiation, the radius convergence remain constant if the series is differentiable and or integrated, of course. But the interval convergence might not stay the same. So, but I mean, at the end of the day, you mostly just consider with the radius convergence for the power series representation, unless you specify otherwise. So some of the problems you might be asked for sure is that express a function as a sum of power series and find the interval convergence. And when I talk about interval convergence, it's kind of the same thing, but this time you don't need to use a ratio test. If you ever use a ratio test, you're going to use that for the original function, and then again check the endpoint. But now when you check the endpoint, you have to check it for the final power series that you derive. Step is to express a series by writing it in geometric series and put it into the form of a power series by maybe derive it or relating it with the some of the basic function that we derive using differentiation or integration. Then you apply the multiplying factor smaller than 1 using the ratio test the multiplying factors to find the radius convergence, and then you just check on the two endpoints. Or another way that you can be asked is to compute the infinite sum of a power series. So it will require more steps. You write it in the form of power series usually in the form of geometric series, and then you're gonna put it in using a over 1 minus r. Remember this for the geometric series? Note the fact here, a is not the center of its power series for us. A here is the first term in the sequence, and r is the multiplying factor. I don't want you guys to make this confusion, because I know like the fact that we use the same denotation for different quantities, but that's how it works. Then we have something that we have got so far, and I think you can easily, so when I say to do well in these sections, you need a very good documentation of what you did in class, is that you have to be able to document some of the basic representation you got so far. Is one some of them is 1 over 1 minus x. Some of them is 1 over 1 minus x squared. Or you can have 1 over 1 plus x. 1 over 1 plus x squared. You can derive these themselves. It's actually really normal. And you have ln of 1 minus x. Or you can find ln of 1 plus x as well. And then you have something like this, which is going to help you find inverse tangent of x by taking one of the integral. Or you can find things like e to the x. What's the representation for that? And I think in the upcoming sections, we're going to learn about sine and cosine. So that's every theory that I have. Some final note, taking derivative will shift n from a to a plus 1. That's what I already mentioned. Taking integral won't change the starting n. That's what I also mentioned. Now, please keep this part in mind because we're going to be using it a lot in the example. So let's start this one. Example 3 is practice problem 2e. Find the power series representation of this thing. Now, you can relate this to, give me a second, get back to that. So you can relate this to as the integral of 1 over 2 plus x dx. Now, so we have ln of 2 plus x is derivative integral of 2 plus x dx. And then what is the representation of this one? It's going to be the series of going from 0 of, so we have 1 over 2 plus x is 1 over, take the 2 out, you have 1 minus x over 1 minus of minus x over 2. Therefore, you have is equal 1/2 the series from 0 to infinity, negative x over 2 to the n, or which can be written as half with the series from n equal to 0 to infinity, negative 1 to the n, x to the n, 2 to the n. Or you can put it in the simplified form. You put this n, this 2 inside, you're going to have this 2 to the n plus 1. Now, you have this sequence. We're going to put it back into here. ln of 2 plus x is going to be the integral of this dx. Now, you take integral of every term except for the constant. So, negative 1 to the n and over 2 to the n plus 1. They're all constant. It doesn't have anything related to x, right? Because you only take it with respect to x. So you're going to have the series negative 1 to the n over 2 to the n plus 1. The integral of x to the n dx, which is going to be x to the n plus 1 over n plus 1 plus c. So that's my answer for this questions. Not too challenging, and it makes good sense of what we're looking for at the same time. When you can find what is c by putting x equals 0. You're gonna have ln of 2 equal to, this entire thing is gonna become 0, so equal to c. So you're gonna have ln of 2 plus x is equal to, so you have this additional step I don't actually mention before, but it's fine. You can usually just plug in a special number to find what is the value of c. Okay, that's my final answer for these questions. So the step is first kind of identify it with a basic type of integration of power series, and then try to do something like maybe integrate it or maybe differentiate it to find the series of another of the related one. Example 4 is going to be compute the infinite sum, and that's what in the power series representations. You guys might have the kind of general idea that we might put it in the form of a power series, use like maybe put it in the form equal to 1 over something minus x or something like that, or to find what is the sum of this power series. And so the way that we're going to do this is that we're going to try to relate it to something that we're familiar with. So let's look again at this slide. You have the only one that you have had so far with the n multiply is this series. So I'm going to try to put it in something like that. We're going to have n equal to 1. So you're going to have n multiply 1/5 to the n minus 1 multiply 1/5, right? Because it's going to be just the same way of writing two different things. So when I take this 1/5 out, you're going to have this series, n 1/5 to the n minus 1. Now looking back up the series that we have had so far, it looks the exact same form, but instead of x, we have 1/5. So basically you put 1/5 in this scenario, and clearly the fact that you can see if x equal to 1/5, this series is convergent, so it makes sense. So I'm gonna have this one equal 1 over 1 minus 1/5 to square. And so this one is gonna equal 25 over 16. And then you forget that's 1/5 at the front. So we do 1/5 again, so it's gonna be 5 over 16. So the key here is to be able to relate this part to an existing series, and that's the entire point of finding the power series representation. So again, I would say do very good documentation of what series you achieved so far. So kind of like when you can come back to relate it, you don't need to track back several pages of what you did and get maybe completely lost of what you already did in the previous days. So be very good documentation about that. Now we'll come to the final example, which is practice problem 2G. Find the power series representation of this. And I would say this one is kind of maybe a challenging one to some people because they might not have been able to relate it to one of the series that we did before. But as I said very clearly, here you can see we have that square there. So we can maybe use that, but we have to put it in the form of just x. So we have 3x over 2 minus 3x squared. And when I say maybe just x, is that, okay, well here you're going to take the 4 out. So what we have so far in the thing is going to have 1 minus 3x over 2 squared. So this thing we're going to have 3x over 4 outside. And we try to find a series of 1 minus 3x over 2 squared, which we're going to now do it. It's going to be the series starting from 1 to infinity. You have n, and then you have 3x over 2 to the n minus 1. That's what we have found so far. And so now you have that series is going to equal 3x over 4. The series from 1 to infinity, and multiply 3 to the n minus 1, x to the n minus 1 over 2 to the n minus 1. Now, this one, I'm just going to plug this thing into the inside. So it's a series starting from 1 to infinity, and multiply 3 to the n, x to the n, divided by 2 to the n plus 1. So this is my power series representation for the function. You can maybe explain it by, you can even go further by finding the radius of convergence. So I'm going to find this. Radius of convergence is going to be limit of n approaching infinity, n plus 1, multiply 3 to the n plus 1, x to the n plus 1, divided by 2 to the n plus 3, and then we have actually 2 to the n plus 2, and then you have 2 to the n plus 1, n, 3n, xn. Now this one, as n going to infinity, n plus 1 over n is just going to be 1. And then you have, this is 3, absolute value of x over 2. Therefore, you get this one smaller than 1, so the radius of convergence is 2/3. And then you can also go further by finding what is the interval of convergence. So here we have the center is a equals 0. So you can check is x equal -3rd. You're going to have a series become n, 3n, -2 over 3 to the n over 2 to the n plus 1, which can be simplified as n multiply -1 to the n over 2, right? Because you have 2 to the n gonna be cancelled out with 2 to the n in the denominator, so you have 2 left. And clearly, as n approaching infinity, this entire thing going to is gonna fluctuate between plus or minus infinity, so it's divergence by test of divergence. And if you do the same thing for 2/3, you're gonna have a series kind of similar. So I'll write over here because it's 2 down in the bottom. It's gonna be difficult for me. So you're gonna have n over 2, and this is also divergent by test of divergence. So our interval of convergence is just from -2/3 to 2/3. So again, the important part is doing relations by differentiation or integral again, or just use one of the series that you found before. If you wasn't able to document this part, you can go from 1 over 2 minus 3x. You can start from here, and when you take derivative of this, you're going to end up with so you have this derivative is going to equal -3 over 2 to 3x squared, right? And so this is how you can relate it to that. And this one can easily go because it's kind of similar to 1 over 1 minus x. You can do that. So that's all I have so far for today. So if you don't have any more questions, I have the practice problems here, and I think it's very helpful. And if you ever need more practice, please feel free to email me. I have more than enough of these. Or you can always look on the website of the math department to find the practice problems for power series. There should be a lot on them because it's kind of like the main focus for the final exam. So if there's no more questions, I'll stop the sessions here, and I'll see you guys next week. Have a great weekend, guys.